In the previous section, we learned what does it mean when we say that functions are first-class values in Reason. In this section, we will discover that all functions in Reason are in reality functions with single argument. This means that if we have a function with multiple arguments, we can apply all of them at once, or we can pass them one by one. And this ability is called the partial application of a function. Let's take a look at the composition example from the previous section again. We defined the add function, which adds 5 to the passed argument. We also defined the multiply function, which multiplies passed argument by 10. And we also have the compose function, which composes two functions together and passes a value to them. We passed add and multiply functions to the compose function. And finally, we pass an integer to this function and we get back the result. Now, maybe you were wondering, how is it possible that we first pass two arguments to our function, bound it to the identifier, and passed the last argument later? Well, in order to understand that, let's rewrite the compose function a little bit differently. We defined the real compose function, which works exactly the same as its first version. The difference is that the real compose function has several functions expecting a single argument and returning another function. And this syntax is the real form of the compose function. The real compose function is just written without the syntactic sugar, which makes our code more readable. So under the hood, the compose function looks like the real compose function. These are two possible ways of creating the same function. As you can see, the version without the syntactic sugar has several functions expecting a single argument and returning another function. So each time we pass an argument, this function returns a new function waiting for another argument and so on. This definition allows us to pass each argument separately. And this is called currying. Currying a function means transforming it from a function expecting one or more parameters, here, to a series of unary function calls. In other words, to a series of functions expecting a single parameter. And this is what Reason does with the compose function. Under the hood, it transforms it to the real compose version. It transforms it from a single function expecting several parameters to several functions expecting a single parameter. So the real compose function is a curried version of the compose function. This means we can pass all the arguments at once or only some of them and pass the rest later. Let's call both versions of our function with the same arguments. And we got the same results. Real compose is just a real form that is behind the syntactic sugar of the original compose function. If we check the types of both functions, here, and here, they are the same, and they also have the same behavior, as you can see. In Reason, functions with multiple arguments are the same as functions returning functions as values. This means that a function with multiple arguments is just a syntactic sugar for nested functions with one argument. In other words, all the functions in Reason are functions with one argument only. So all the functions in Reason are automatically queried. And because of this feature, we can partially apply functions in Reason. This means that if we have a function with multiple arguments, we can apply all of them at once, or we can pass them one by one. And that's what we did in our example. We partially applied both functions. We first passed two functional arguments, here and here, and later we passed the integer value as the last argument. As a result, we can pass any integer to our function composition, and this function will pass this integer to multiply and add functions. This means we can reuse this function composition throughout our program. Let's take a look at how the partial application can help us to write more concise code. We tackled our example a little bit. The multiply function now expects two integer parameters, a and b. Let's say we would like to pass one of its parameters in advance. Without the partial application, we would need to create another function for that before we can pass it to the compose function. And that's what we did in this example, and we call this function multify. It takes a single parameter and passes it to the multiply function, which already has an integer passed to it as its first argument. Now we can pass this function to the compose function. And then we pass an integer and we call it, and it works. However, it's pretty verbose. So let's take an advantage of a partial application and rewrite this code. As you can see, we don't need to create an additional function anymore. We just pass the argument directly to the multiply function when calling the compose function. And everything works the same. So the partial application helped us to write more concise code. Maybe you're wondering what happens when we partially apply a function, just as we did in the previous examples. When exactly is the function evaluated by the compiler? Let's take a look at an example. We defined the add function, which expects 3 integers and returns their sum. As we already learned, we can pass these arguments separately or all at once. Let's call our add function. When we pass all 3 arguments to the add function, its body gets evaluated and we get the result. However, how is our function evaluated when we partially apply it? Let's take a look. We passed a single integer argument to the add function, and we got back a new function expecting remaining 2 arguments. And we bound this function to the add5 identifier. This means that our function hasn't been evaluated yet. This is because of the functional arrow symbol, which plays an important role during the evaluation since it blocks any function evaluation. This means when we pass an argument to a function which expects several of them, like our add function, the evaluation cannot continue until the arguments preceding the arrow symbol are passed. In other words, the evaluation of the function can continue only when all the expected arguments are passed. So let's pass them. First, we pass another integer argument separately, and we got back a new function expecting one last argument. Then, we passed the last argument as well. Since all the expected arguments were passed to the function, it got evaluated and we got our result. Let's take a look at another illustration. We defined the toInteger function, which expects 2 strings and converts them to an integer. As you can see, even before we pass any arguments to the function, we know that it will crash, since we are converting a string, which can't be a valid integer because it's composed of letters. Nevertheless, the compiler accepted our function, and it's telling us that it expects 2 strings and returns an integer. The compiler doesn't know about the error since our function hasn't been evaluated yet. Let's try to pass the first string argument to our function. We passed a string to our function, and we got back a function expecting the second argument. And we bound it to the partially applied identifier. As you can see, we still have no error. This means that our function still hasn't been evaluated. This is because we still haven't passed all the arguments required by the toInteger function. Let's pass the final argument. We passed the last string argument to the partially applied function, and we got a runtime error, since our function has been finally evaluated and the compiler figured out that we can't convert our string to an integer. So this proves our point that functions are evaluated when all the expected arguments are passed. However, what if we want to partially evaluate our function? Is that possible in Reason? Let's take a look. We defined the concat_lists function, which expects 3 lists and concatenates them together using the built-in list.append function. First, we passed 2 list arguments here, first one and second one, and stored this partially applied function as partially applied. Then we passed the remaining list argument here and we get back the concatenated list. This approach doesn't affect evaluation of the function in any way. Function will be evaluated when we pass the last argument, as we did here. As you can see, this function is performing two separate concatenation operations. First, it concatenates list 1 and list 2, and then it concatenates this result with list 3. In some cases, we might want to evaluate these operations separately. In other words, we would like to pass two list arguments to our function and evaluate their concatenation. And later, we would like to pass the remaining list argument and perform the final concatenation. And this is called partial evaluation. Let's take a look at an example. We defined the concat_lists partial function, which does the same thing as the previous function. However, we changed its definition by pulling the first concatenation operation out to the separate function evaluation. So when we pass the first two list arguments, they will get concatenated here and stored as new list. And we will get back a new function waiting for the last argument. Let's call this function. Now, our function gets evaluated in two phases. The first part of the function is evaluated when we pass the first two list arguments here. This means that these two lists are concatenated and the result is stored as new list. The second part gets evaluated when the last argument is passed here. And when this happens, it gets concatenated with the new list. This is possible since we have the new list identifier inside the closure. This means we can still access it here. So by using partial evaluation, we get more control over functions evaluation. This means we can make our functions more efficient, since we can evaluate different parts of a function at different places in our program.